Hello, welcome back to the second course in physics. And in this lecture, we will continue talking about the methods of circuit analysis and the various theorems relevant to this field. The contents of this lecture will still focus on the equivalent circuits, and we will, in that sense, discuss a number of theorems. Thevenin's theorem will be first addressed, and then the theory of maximum power transfer, and then after that we will take an application and consider the unbalanced Wheatstone bridge and solve it using the developed technique. After that, we will be considering another theorem, which is Norton's theorem in the field of equivalent circuits and circuit analysis. After that, we will touch on some applications. So we'll consider a circuit and apply the general techniques that we have studied. And finally, we will address another theorem, which is the superposition theorem, and the way of how we apply this theorem to circuit analysis. And in the beginning, we will talk about Thevenin's theorem and Thevenin's equivalent. This theorem states that any linear network that is composed of a number of resistors, ohmic resistors, of course, linear resistors, and electromotive forces, any such network, no matter how complicated it is, can be replaced by a single electromotive force with an electromotive force epsilon sub th, that is Thevenin, that goes for Thevenin, epsilon Thevenin, and a single resistance R sub Thevenin in series between any 2 points in the network. That is, if we have a very complicated network, we can select any 2 points we desire. For example, if we need to calculate the current through a given resistor or a given device, so we take the terminals of that device, the 2 points of the circuit where that device is connected, and we remove these two points, and we consider all the circuit inside as a black box, the whole circuit as a black box connected to this load, to this device. And that black box, we can analyze it considering the Thevenin's equivalent as we will be discussing. So what do we do in that sense? For an example, we consider this circuit that we have discussed before, the double node circuit, and suppose that we are interested in calculating the current through the branch R2. In that case, we take the points that are shown here at the beginning and the end, and we consider everything else is in a black box, inside a black box. So we have epsilon 1, R1, and R3 are like in a black box with the terminals are free. So this is the equivalent circuit, free terminals, and inside the black box, instead of having all this number of resistors and electromotive forces, we consider that they are equivalent. Everything here is equivalent to a single electromotive force, epsilon Thevenin, and a single resistance, R Thevenin, in series. So this is the equivalent, Thevenin's equivalent. And then after that, we can hook with this Thevenin's equivalent, with this black box, after we know its behavior, meaning after we calculate epsilon Thevenin and R Thevenin, we can connect it with any load. And after we connect this black box with any load, we know the behavior of this black box. and then we can determine the behavior in the circuits. This is the philosophy. So how do we determine the equivalents? We determine them by, first of all, we take an open circuit across these 2 points. The open circuit will give on the one hand the potential difference between these 2 points, which is V minus 0. We consider that this is a 0 as a reference, or simply the difference in potential between these 2 points, which is here V. That's the potential difference between these 2 points. In the open circuit geometry, this is V, the difference in potential. And since the circuit is open, so there is no current flowing, that means the potential difference V is the same as epsilon Thevenin. It's the same as epsilon Thevenin. So epsilon Thevenin is equal to V. That's from the Thevenin's equivalent. Now, let's go to, this is just an example, this circuit. This philosophy can apply to any circuit, of course, but as an example, we are considering this circuit. If we apply this, the potential difference V between these 2 points, which is between this node and between this node, this potential difference in the open circuit, in this case, in the open circuit, there is no current flowing outside the black box. That means the circuit is flowing in this loop. In this loop that's consisting of epsilon 1, R1, and R3. So in this case, V is equal to simply the potential across R3, which is I3 times R3. So that means if we equate these 2 circuits, and as we said, the equivalent circuit must exactly simulate the behavior of the original circuit. If we do that, then epsilon Thevenin, which is the potential difference between these 2 nodes, which is V, is exactly equal to I3 R3. That is obtained from the open circuit geometry. And now, secondly, how do we determine R Thevenin? That is how to determine epsilon Thevenin. Now, to determine R Thevenin, we assume that in the box there is no source. There are no sources. So we set all the sources in the box, in the Thevenin's equivalent, and in the original circuit. We set all the sources equal to 0. So in this case, epsilon Thevenin in the Thevenin's circuit, epsilon Thevenin is set equal to 0. So the total resistance in the box is simply R Thevenin. On the other hand, in the circuit that is in hand, that we are applying our argument to, in this circuit, we set the sources equals to 0. That means epsilon 1, we set it equals to 0. So what do we have in terms of resistance in the box? We have R1 and R3 in parallel. So that means R1 and R3 in parallel in the original circuit should equal to R Thevenin in the Thevenin's circuit. So applying these concepts, we have I1 is equal to I3 in the open circuit geometry, because the current only flows in the one loop. We have an open circuit, so the current is not flowing outside into R2. And thus, this I1, which is equal to I3 in the open circuit, is equal to epsilon 1 over R1 plus R3, and from which epsilon Thevenin is determined, which is V, simply V, which is I3 R3. So this I3 times R3 is equal to epsilon Thevenin. And that is how to determine the Thevenin's electromotive force, one of the Thevenin's equivalents. And now, in order to determine the resistance, the Thevenin's equivalent of the resistance, R Thevenin, we set the, as we said, we set the sources to 0 in the original circuit and in Thevenin's equivalent circuit, and that gives you R Thevenin is equal to R1 and R3 in parallel. R1 and R3 in parallel, the equivalent resistance for it is simply R1 R3 over R1 plus R3, as we learned before. So R Thevenin should be equals to should equal R1 R3 over R1 plus R3. Thus, we have determined the 2 Thevenin's equivalents, which are epsilon Thevenin and R Thevenin. And now we have like a box, we have like a box in which the electromotive force and the resistance are known, and they are in series. So we have a very simple equivalent circuit. We can hook this circuit to any load, to anything outside, to any device, and the behavior is completely determined. And for example, if we go back to our original circuit, we have determined the Thevenin's equivalence. We hook now this box to the branch across R2, and we can thus determine the current through R2 by hooking this box to this remaining branch. We have the current that flows in the loop is simply epsilon Thevenin. We can go around the loop. Epsilon Thevenin minus epsilon 2, that's the total electromotive force across the loop or around the loop, and divide this potential difference, which is simply the summation of the electromotive force taking into consideration the signs, divided by the total resistance, which is R Thevenin plus R2. So this determines the current, and this current is the current flowing through R2, resistance R2. So putting these together, replacing epsilon Thevenin by its value, and replacing R Thevenin by its value, we obtain I is equal to R3 times epsilon 1 minus epsilon 2 times, in parentheses, R1 plus R3 divided by R1 R2 plus R2 R3 plus R1 R3. So this is the current I that flows through the Thevenin's resistance and through R2. And this result is exactly the same result, this current that is obtained by Thevenin's theorem, from the application of Thevenin's theorem, is exactly the same result that we obtain from the node analysis. We recall the V that we have obtained from the node analysis previously, and we recall that I2, the current through R2, is simply V minus epsilon 2 over R2. V minus epsilon 2 over R2 from the node analysis is equal to I2. If we substitute for V as we have determined previously, we can obtain I2, which is exactly the same result that we obtained from Thevenin's theorem. Conclusion, the Thevenin's equivalence can be determined for any steady-state network with respect to any two external terminals, any 2 points in the circuit. And thus, we have all the information about the behavior of the network when another network is attached to the terminal. And this, by this example, we see a very simplistic example of the application of such powerful theorem. And now we move to consider another theorem, which is called the theorem of maximum power transfer. Now, the question that arises is the following. As we have determined the Thevenin's equivalent. If we have a complicated looking circuit and we replace it by a box and with the terminals from the box, two terminals from the box, and that box contains Thevenin's resistance and Thevenin's electromotive force in series. Now, the question is, if that box is connected with a load resistance, what is the amount or the magnitude of the resistance that we attach to the box that would ensure that we have a maximum power delivered to that load? How can we select the resistance, the load resistance attached to the box to obtain maximum power delivered through that load? That is the theory of the maximum power transfer. And we recall that the power through the load resistance, which is R2 in our previous example, we have connected with Thevenin's equivalent R2. This power is simply I2, the current through the resistance, I2 square times the resistance R2. And this is of course a general theorem, but we are taking an example, applying it in order to illustrate how to apply this theorem. But this is a general theorem. So we take the current through that resistance, which is epsilon Thevenin minus epsilon 2 over R Thevenin plus R2. That's the current flowing through the resistance R2, all square, as we obtained before, times R2 times the resistance. That's the power. And now, in order to obtain the maximum power, we set dP by dR2 is equal to 0. And from this relation, we determine R2. R2 that will give maximum power transfer. And this, we solve for R2, and we obtain, if we take the derivative and we solve for R2, this will give us R2 is equal to R Thevenin, which means that if we have a complicated network, the load resistance that we can attach to this box, to this complicated network, will receive maximum power delivered to it if only the resistance of that device that we attach to the network has a resistance. If the resistance of that load is equal to the Thevenin's equivalent resistance of the network. That is the theorem of maximum power transfer. And now we will discuss the Wheatstone bridge, the unbalanced Wheatstone bridge, as an example of Thevenin's theorem and how we can apply it to solve complicated circuits. And we recall the Wheatstone bridge, which consists of these two delta shapes of resistors connected in this complicated manner. And we are, if the bridge is unbalanced, that means current is flowing between the points C and D in RD. In this case, previously we have discussed the case of the balanced bridge in which there is no current, ID is equal to 0. But here we consider a general case if ID is not equal to 0, and we are concerned with the calculation of ID, I across RD. So how do we do it? If we want to use Thevenin's theorem for simplicity, we take the points C and D as the free points, and the remaining components will be the network, our network. So we take as the free ends C and D. So this will give us this. C and D are the free ends, and all the remaining components, R1 and R2, R3 and R4, together with epsilon, are all included in the box, which we will try to find the Thevenin's equivalents for it. So this is how we have. And now if we replace this complicated network by a Thevenin's equivalent of epsilon Thevenin and R Thevenin, then we have a simple equivalent circuit, and we can attach it to RD, and we can very easily determine the current ID. That's what we do. So use Thevenin's theorem in this case. In Thevenin's theorem, the open circuit geometry, if we have an open circuit, that means there is no current going through C or through D outside the box. That means the currents will flow as shown in here. We will have an I prime flowing through the first loop, the top loop, and we will have I flowing through the second loop. And in order to calculate Thevenin's equivalent, remember that the potential difference VCD is the voltage across this between C and D, and that voltage in the open circuit geometry, this voltage drop is the Thevenin's electromotive force. So in order to determine VCD, we have to calculate I prime and I in order to be able to calculate VCD. And that's what we are doing here. So I prime is equal to, simply from this loop, is equal to epsilon over R1 plus R2 using the Kirchhoff's laws. And similarly, I is equal to epsilon divided by R3 plus R4, also using Kirchhoff's laws. So this is I1, I prime, and I. And now, in order to determine Thevenin's equivalent, we recall that epsilon Thevenin is the potential VCD in the open circuit geometry. And that is equal to, as we go from C to D, we go from C to A first across R1, and that is equal to minus I prime times R1, because as we go from C to A, we're going against the current. So this is minus I prime R1, and here from A to D plus I times R3, because we are going with the current. And so this is epsilon Thevenin. And now we substitute for the values of I1, I prime, and I. So substituting for these, we'll get epsilon Thevenin is equal to I times R3, which is epsilon R3 over R3 plus R4, minus I prime R1, which is minus epsilon R1 over R1 plus R2. So this is simply epsilon Thevenin. And now we consider the Thevenin's resistance. In order to calculate Thevenin's resistance, we recall that we set all the sources equal to 0. And here we had epsilon. We set that equals to 0, and we then calculate the Thevenin's equivalent resistance. So if we set this equals to 0 and we look at the circuit will consist of R1 and R2 in parallel, and then we have R3 and R4 in parallel. And this R1, R2 in parallel, they are connected in series with R3, R4 in parallel. So here we have two resistors. The first set is R1, R2 in parallel. They give an equivalent resistance of R1, R2 over R1 plus R2, as we have learned before. And R3, R4 in parallel, they give R3, R4, the equivalent resistance of these two in parallel is R3, R4 over R3 plus R4. And these two sets are in series with each other, because this point is connected to R1, R2, and this same point is connected to R3, R4. So the total Thevenin's resistance is simply the first resistance, R1, R2 over R1 plus R2, plus the second resistance in series, R3, R4 over R3 plus R4. So thus, we have calculated R Thevenin, and we have calculated also epsilon Thevenin. These are the Thevenin's equivalents. And now, once we have obtained Thevenin's equivalents, we have a very simple circuit, Thevenin's circuit, which has R Thevenin and epsilon Thevenin in a box. We don't care what is inside the box. This box replaces the complicated looking circuit that we had. We connect now this from the free ends, C and D, if we recall. We connected with RD, and we calculate the loop current. The loop current is the current actually flowing through ID. So the current through ID is simply equals, from the loop equation, is equal to epsilon Thevenin over the total resistance across the loop, which is R Thevenin plus RD. Now, substituting for these values, for epsilon Thevenin and R Thevenin, as we have obtained, we will get ID is equal to epsilon times R2, R3 minus R1, R4 over R1, R2 times R3 plus R4 plus R3, R4 times R1 plus R2 plus RD times R1 plus R2 times R3 plus R4 in parentheses. And this gives us the result of ID. It is a complicated looking formula, but it was dramatically simplified by the use of Thevenin's theorem, and you can know how much this problem was simplified if you try to solve the problem using the branch analysis technique, for example. Now we go to Norton's theorem, which is another theorem that would take into consideration equivalent circuits in order to simplify circuit analysis. And this theorem states that any linear network composed of resistors and electromotive forces can be replaced by a single current generator in this case, in parallel with a single resistance R sub n between any 2 points in the network. So, similar to Thevenin's equivalence, any complicated looking network can be replaced, like a box, can be replaced with a box. Inside the box there is a current generator in parallel, connected in parallel with a resistance. The current generator provides I sub n, current, Norton's current, Norton's equivalent current, and the resistor in parallel has a resistance of R sub n, which is Norton's equivalent resistance. And now this is a very simple circuit, a current generator and a resistor in parallel. We can connect it with any load or device outside, and the behavior of the box or the Norton's equivalent is understood, and the Norton's equivalents are determined. Then we can determine the circuit properties this way. So what do we have? We have a box in general for the equivalence. We have a box of linear network consisting of linear ohmic resistances and electromotive forces and current generators. And this can be replaced in the Norton's theorem by Norton's equivalent, which consists of a box, of course. Inside the box there is a current generator providing I sub n and a resistance R in parallel with Rn, Norton's equivalent resistance. This can be viewed, as we have mentioned before, the same network can be also constructed using Thevenin's theorem, and the Thevenin's equivalent, as we have discussed before, is simply a box that consists of R Thevenin and epsilon Thevenin in series. Of course, because it is the same network, and we have said before that each equivalent circuit should simulate exactly the original circuit, that means that the Thevenin's equivalent circuit and the Norton's equivalent circuit should be exactly the same, should simulate the same behavior, because they are equivalent to the same network. So in general, that means the Thevenin's equivalent circuit has exactly the same behavior as the Norton's equivalent circuit. And comparing these two together, we can determine the Norton's equivalence in terms of Thevenin's equivalence, actually. And thus we can understand fully the behavior of the Norton's circuit, equivalent circuit, just like the way we understood the Thevenin's equivalent circuit. And this can be done this way. So we know that these two circuits are equivalent to each other, the Norton circuit and the Thevenin circuit. So if we have, for example, if we short circuit those two open terminals across both circuits in the Norton's theorem and in the Thevenin's theorem, if we short circuit them, then the current in the first circuit, in the Norton's circuit, the current will flow from the generator across the short circuit, and it will not flow through Rn, because Rn is a resistance, and since the circuit is shorted, so In will be flowing across from this point, the first point, to the second point, across the short. So this I, that means flowing, if we short the circuit, the current that we draw from that circuit, if we short the circuit, is simply In. So I that we draw from the circuit, if we short it, is simply the current of the equivalent generator, of the Norton generator. Now, since the two circuits are equivalent, if we short circuit the Thevenin circuit now, what do we get? We get a current that flows, because we have a loop now that consists of epsilon Thevenin and R Thevenin. That's it. So the current that flows in the circuit, or that's drawn from this box, is simply epsilon Thevenin divided by R Thevenin. And since this circuit and the previous circuit are equivalent, that means this current is exactly the same current we can draw from the box, whether we look at this box as being Norton equivalent or Thevenin's equivalent. That means I is the same as I Thevenin. And now, secondly, we are after the second equivalent, which is the resistance, R sub n. R sub n is measured, of course, in both cases, if we set the sources as equal to 0. The sources are equal to 0. In Norton's equivalent circuit, we set the current generator, IN, equals to 0. And in Thevenin's equivalent circuit, we set epsilon Thevenin is equal to 0. So if we set these and we look at the resistance in each case, then the resistance in the upper case is equal to the resistance in the lower case. The resistance in the upper case is simply Rn, and the resistance in the lower case, in Thevenin's case, is simply R Thevenin. So that means the Norton's equivalent resistance is equal to Thevenin's equivalent resistance. And now we apply these concepts to real circuits, and let's assume that we have this sort of not so simplistic circuit with a current generator with a resistance in parallel with the current generator R1, and electromotive force epsilon connected with R2 and then connected with R3. And now, if we are in this circuit, if we are interested in calculating the current across R3, across the resistor R3. In this case, what do is we consider Thevenin's equivalent. In Thevenin's equivalent, we consider we have a black box that contains all the components, and we consider the terminals of R3 as being the open terminals to which we can hook the resistance R3. So this is the Thevenin's equivalent, and in order to determine Thevenin's equivalence, we consider first of all the open circuit, and in the open circuit we have this voltage across these 2 points. The voltage is simply equals to epsilon, which is the electromotive force, and here minus J times R1, because in the open circuit the current is flowing in this loop only. J is flowing in this loop, and the potential drop between this point and this point is equal to J times R1, but this potential drop, it goes from positive to negative, and here it's going from negative to positive, going across this branch. So the direction of epsilon is opposite to the direction of the potential provided by the current generator. So the total voltage difference is simply epsilon minus J R1. That is epsilon Thevenin. That's the potential difference between these 2 points. And now, in order to calculate the Thevenin's resistance, we assume that we have no sources. That means epsilon is 0. We set epsilon 0, and we set J is equal to 0, and we look at the remaining resistance. The equivalent resistance is R Thevenin, which is simply equals to R2 plus R1. And now we have this box that contains the Thevenin's equivalents, R Thevenin, epsilon Thevenin, that we have just determined. And now we hook this box, the Thevenin circuit or equivalents, we hook it to R3, and by hooking it to R3, we can determine very easily I3, the current flowing across the load R3. And this is simply equals to the voltage, which is epsilon Thevenin divided by R Thevenin plus R3. And we substitute for epsilon Thevenin and for R Thevenin, and we obtain the result I3 is equal to epsilon minus JR1 over R1 plus R2 plus R3. This is a straightforward example of the application of Thevenin's theorem. And now we consider Norton's theorem applied to the same problem. And here we have the circuit in a box, and we consider that that this box is equivalent to a Norton's equivalence. In order to obtain the Norton's equivalence, IN and RN, first of all, we short circuit these two terminals of the box. That means V is equal to 0 by short circuiting it. And thus we obtain IN in the short circuit. IN is equal to epsilon minus J sub R, JR sub 1, which is simply the voltage difference divided by R1 plus R2. That is I that flows across the circuit after we short circuit it, because as we knew from before, I that flows in this short circuit, I is IN, and that is I, which we determine by going around the loop. And now, in order to determine the equivalent resistance Rn, we set no sources, and in no sources, Rn is equal to simply the resistance if we set epsilon 0 and J, the current generator, equals to 0. We will have simply R2 and R1 in series, and Rn is equal to R1 plus R2. And this is the Norton's equivalent, a current generator providing IN in parallel with a resistor Rn, and we have R3 as the load, and determine I3 across the load. I3 is thus equals to epsilon minus JR1 over R1 plus R2 plus R3, which is exactly the same result that we obtained from Thevenin's equivalent. And now let's move to another theorem, which is the superposition theorem applied to circuit analysis, and we can see how we can apply this theorem to determine the properties and to analyze the circuit. And this theorem states that the current delivered by the various sources in a circuit are independent of each other. So if we have a circuit with a number of sources, current sources or voltage sources, power sources, each one of them would deliver currents through the circuit in an independent manner. So we can always determine the current provided by one source, setting all other sources to 0, and determine that current, and then move to the second source, setting all other sources to 0, and so on. And then we can add up these currents, and this is simply the superposition principle or the superposition theorem. So the currents can be calculated by adding the effects of the individual sources separately. And as an example, consider this circuit that we have just solved using Norton's equivalent and Thevenin's equivalence. And we have two sources here, epsilon and J. And in the beginning, we set the current generator as being absent. J is equal to 0. And we will have a circuit which has epsilon in series in a loop, in series with R1 and R2 and R3. So the current set up by epsilon is simply epsilon over R1 plus R2 plus R3. That is the contribution of the electromotive force. And secondly, we set the epsilon equals to 0, and we calculate the effect of the current generator. considering that the current generator provides voltage that is in opposite direction to epsilon, so we have this minus sign here, and I is the voltage provided by the current generator, which is minus JR1, divided, this is in series with the resistors R1, R2, and R3, divided by R1 plus R2 plus R3. And now we have two sources with two contributions. If we add up these two contributions, according to the superposition theorem, we obtain I3 is equal to epsilon minus JR1 over R1 plus R2 plus R3, which is exactly the same result that we obtain by using Thevenin's theorem or Norton's theorem. And this equivalence should be expected and should be there, because we are dealing or we are analyzing the same circuit. So no matter what method we are using for analyzing the circuit, we should arrive at exactly the same answer. And this is what we have obtained by using the different techniques. At this point, I end my lecture, and I thank you for your attention.